we're going to touch a little bit on the topic of fluid dynamics. And the things we're going to talk about are how fluid flows. So we're going to talk about the rate of the fluid going past a certain point. So if you can imagine a marker, kind of seeing how much of the liquid or gas goes by. And we're also going to look at Bernoulli's equation, especially where we look at the idea of conservation of energy. And Bernoulli's equation is important for fluids because it relates pressure and velocity. It gives us something to work with to find one thing or the other. So starting with flow rate, if you have some sort of a tube, a hose perhaps that has a cross-sectional area, which is if you sliced it, what it looks like on end, and it's got some amount of water flowing through it, then the flow rate is just equal to the volume of that tube divided by the elapsed time that the water flows through, or the liquid flows through. Be careful when you're using the units, because a lot of times you'll get the flow rate in liters per second, and we really need that to be in meters cubed per second if you're trying to find velocity in meters per second. So just watch for that. So, like I said, flow rate is a measure of how much water flows by in a certain time period. And velocity and flow rate are different. Velocity is how fast the water is moving. Here's a different way to find your flow rate. If you have the velocity of the water and the area, the cross-sectional area of the tube, then you can also find the flow rate. An interesting thing about most fluids, not all of them, but most of them, is that they're not compressible, which means that you can put pressure on it, but the volume doesn't change. Some will. But for fluids that are not compressible, the fluid flow rate doesn't change when the shape of the pipe changes. So what happens is, as the pipe gets smaller and smaller, the area gets smaller and smaller, the speed of the fluid increases to make up for that change. So the flow rate always stays the same. So for Bernoulli's equation, like I said before, it provides a relationship between pressure and velocity in fluids. And looking at the equation, I think you can see some similarities between this and total energy. You've got something that kind of looks like kinetic energy and something that looks a little bit like potential energy. So the height of the liquid's going to matter. The capital P is called absolute pressure, and remember that's the total of the air pressure and any gauge that's measuring the pressure. The rho is just the density of the fluid. H is the height above a chosen reference point. So you've got one fluid that's at one height and another fluid at a different height. Pick one to be 0. Might make things a little bit easier. So that's just a quick introduction to some of the equations and concepts. We'll work a little bit on this, and I do have an example in a different video for you. Alrighty, bye-bye.